Avishai Ish-Shalom, and I am an independent researcher, consultant. I'm doing all kinds of stuff. If you're interested in that, you can come talk to me after. Most of what I do in the last few years is performance, scale, that kind of stuff. So I'm here to talk to you today about backpressure. If you don't know what backpressure is, you're going to find out through this presentation. And specifically in Node, because it's in a synchronous framework, it's in a synchronous runtime, this is a big problem, actually. So that's basically why we're having this talk. So without further ado, this is an example. It's mostly from the documentation of Node.js. So I took this code snippet basically as is. And this code contains a bug. Okay, it has a problem. So I'm going to give you like 20 seconds to see if you can find what's wrong with it. So basically it reads data from a file, gzips it, puts it into another file. Yeah? Anyone? No? So if you run it, this is what you're going to get. You're going to get out of memory. And long before you get out of memory, you're going to see a lot of memory usage, excessive memory usage. You're going to see garbage collection problems, so on. So why is this happening? Why do we have this kind of problem? So this is basically what's happening. What we have is a very fast reader, which reads data as fast as possible from the file. And we have a slow writer. And because the writer writes the data slower than the process reads the data, it basically accumulates a lot of data in RAM, in memory, in a buffer. So that's basically the problem. We have a mismatch between the rates of the reading, the data input, and the data output. And all the data that we read stays in the heap, in the memory, and this is why we get out-of-memory errors. Okay, so that's basically the problem. We have a slow writer that writes. Okay, so yeah, if you actually go to production environments and see this problem in many cases, in a lot of places, you see excessive memory usage, you see services that are crashing, you see a lot of killers. If you have Kubernetes, you probably know what I'm talking about, and so on, so on, so on. It's a very common problem in many places, but long before you see those, really big, obvious problems, you see slowdowns, you see performance issues, stuff that is like more minute, so to speak. So what's going on? This is a simulation. Okay, this is an actual simulation that's running in the browser. And as you can see, when you have a mismatch in the rates between few stages of processing, or could be services, doesn't matter, same principle, this is basically what happens. Okay, so the excess load is being accumulated in one of the stages, and it will consume more and more load until eventually it will crash or it will have performance problems. We're going to speak about that in a bit. So that's basically what's going on. Okay? This can happen in a number of cases. It can happen if you have a consumer and a producer connected back-to-back. Think about Kafka, for example. It can happen if you have multiple services, like microservices, talking to each other, and one of them is slower than the other. It can happen if you have a database that is slower than the web server, which is often the case, and so on, so on, so on. You get the idea. It can also happen within your node process if you have several functions calling to each other, and one of them takes more time to process, or if you're forking a lot of microtasks. We're going to talk about that in a bit. So between the consumer and the producer, you always have a buffer, and this is where all the data is accumulated, all the pressure is accumulated. So if you have multiple services, you saw in this example, where is the buffer where the requests are stored? Like, what's consuming the memory here? So as it turns out, if you zoom into this kind of system, in between service A and the database, there is the handler function where your code is actually executed and where you actually do stuff. And between service A, service B, and the handler function, there is some buffer, right? Like the requests have to be there before the handler actually executes them. Okay? So where is that buffer? Think about that for a second. Where is that in your node process? So the event loop is that buffer. Okay? So if you don't know how the event loop works, I gave a talk in 2021 here at NodeTLV, termed Q theory for node engineers. And I explained everything about how the event loop works with the different processing phases and all that stuff. But just to give you the highlight, the event loop basically iterates between different execution phases, and in each execution phase, it takes some callback to run from a queue, from a buffer. And each phase has its own buffer, and the tasks that it takes from that buffer, that's known as a microtask. So when you write code in Node.js, whenever you have a wait, or let's say a promise, or a callback, or something like that, that is a microtask. And that is the fundamental execution unit of Node.js. So when you have a microtask, it's getting queued in one of those buffers of the execution phases, and the event loop basically takes it, processes it, takes another one, processes that again and again and again in a loop. That's why it's called an event loop. Okay? So what is the size of those buffers? It's unlimited, yes. So that means it can consume all the memory of your node process until you run out of memory. And this is basically where the load accumulates if you have something that is slower than the previous stage. Okay, so that's the buffer that you see here. So now that we understand what's going on, we can look at how to monitor this. We have in Node, since Node 12, a metric specifically designed for this. It's called event loop utilization. So if the event loop ever blocks, it will not be able to handle the microtasks as fast as they come into the queue. It will not be able to drain this queue. And this you can see by looking at the utilization. Okay, so if the utilization is very high, it means that the event loop is busy all the time. It can't keep up with the rate of microtasks. So perf hooks, that's the model in Node.js where you have this metric. And this is basically how you get this metric. Event loop utilization has three separate metrics. It has a counter for the idle time. It has a counter for the processing time that actually processed stuff. And it has utilization, which is a number between 0 and 1. Okay, it's like a percentage. There is another important metric that is not provided by Node itself, but you can easily generate it. That's the event loop lag. What is the event loop lag? Let's say you have something that is supposed to happen every second, but because the event loop is busy, it's not being executed after a second, it's being executed after a second and a half. That half second extra, that's the event loop lag. And we can measure it exactly like that. We run some callback at some preset interval, in this case 10 seconds, or sorry, 1 second, and we measure when it was actually executed as opposed to when it was supposed to be executed. So just to give you, well, it's supposed to run, 1 second. So this is a demo. Okay, this is an actual code that I wrote that overloads the event loop, and you can see the utilization going up. And when it reaches a certain point, event loop lag starts to rise really fast. You can also see it's unstable, which is what happens when Node goes into overload. So, yeah, really bad numbers here. Event loop lag of almost 1 second in this case is basically an outage. Okay, it means that everything that Node is supposed to be executing is being delayed by 1 second. If you think about your web transactions that may be supposed to have a latency of 200 milliseconds, they all get delayed by 1 second or even more. So those buffers that we have inside of the event loop, they are all, from a mathematical perspective, they are queues. We have a mathematical theory that basically models how those things behave. It's called Q theory. I'm not going to go too much into that. Like I said, I gave a talk about this 2 years ago. You're welcome to look it up 3 years ago. But what you need to know is that buffers are essentially queues from the point of view of the behavior. And the way queues behave is like this. Okay, so we have the utilization metric, remember from 0 to 1. And this is a graph that relates latency or the queue size to the utilization. And then, as you can see, when utilization approaches 100%, okay, even long before that, so around 0.7, it starts to rise very, very fast. It's a non-linear rise. So it will go to infinity when you approach overload. Okay? This is why you cannot run systems at the edge of their capacity. If you run systems at 90% utilization, you will have a lot of latency, you will have out of memory, and so on, so on, so on. So the problem is, because it's non-linear, once you start getting into overload, effects will be very extreme really, really fast. So we need to be careful with this. We also need to make sure to limit all the queues, because otherwise, again, we'll go into that overload. So what can we do? That's really the question. We need to manage load. Okay? So simplest answer to this is a pool-based system. Think about SQS or stuff like that, or even a Kafka consumer. What's nice about a pool-based system is that you cannot overload it, because the worker basically dictates when it will receive traffic. Okay? It says, I'm ready to receive work now, please give me work. Okay? So the worker will never be overloaded because it controls the rate of the work that it gets. But what's the problem with this? We can't use it for HTTP servers, because HTTP servers basically get the load in push. Okay? So we can't manage the load like that. It's really nice, but not all systems are queue-based, not all systems are pool-based. So what we do instead is we basically glue two systems together. We glue the push and the pull system together, and we get this system where you have acts. And this idea is that I get a job, and you don't send me another job before I sent you an act that says I finished the previous job. Okay? So it's like a token that says I can get more work. And then the flow is, I get a job, I handle it, I say, okay, I'm done, send me another job, and so on, so on, so on. This is a signaling system, and this system is called a Kanban. So the Kanban that maybe you heard of it from Agile, that kind of stuff, that's basically a load management system. It was invented by Toyota in the 50s, a long time ago, and actually in engineering, in software engineering and hardware engineering, we use it all the time. And it's the same idea. Basically, it's a receipt, a token that we send back to say we can get more work. Okay? So that's the idea. Many protocols like TCP and HTTP and a lot of other protocols have this built in. So if you heard of the TCP window and the TCP axe, that's basically what they do. It's a Kanban system. And this is the way that we want to build all of our systems, so that we will have built-in load management. So this is basically the way that it works. We have a bunch of stages, processing stages, connected to each other. And we want each of them, when they get load, to send that load to the next stage and the next stage. And when that next stage is done, it will send back the tokens that says, I'm done, send me more work. The next stage will do the same, and so on, so on, so on. We have what is known as a backpressure chain. Okay? The backpressure, the forward pressure is the load, the backpressure is the acknowledgement tokens. And we need to preserve that system throughout this chain, throughout the entire system. Okay, so if you think about microservices, for example, let's say you have 3, 4, 5, 6 microservices talking to each other, and then there's a database at the end. We need to make sure all of them preserve that backpressure chain. That means that I send load to the next service. I don't send more load before I get acknowledgement. That next service does the same, and the same, and you get the point. Okay? This is very important. If we don't do this, then somewhere down the line we will have overload, and the gateway where we receive traffic from the users will not be able to do anything, because it won't know some component in the back was overloaded. So it will just keep on receiving traffic and won't stop the traffic even though there's overload in the back. So we can go back to our original example and see how it should have been written. And the main difference here is that pipe thingy. Okay? This is Node.js streams. Okay? Highly recommend that you look at the API. And Node.js basically provides a very comfortable API for I/O, okay, both network I/O and file-based I/O, that automatically manages backpressure for you. So if you use pipe or pipeline, it will basically do that for you. And the way that it does this is that the write method has return value, which is Boolean. It has a true and false Boolean, values. The true value basically means send more traffic. Okay, the buffer is not full, you can send more and more load. And the false value is basically saying, that's it, I cannot receive more traffic because the buffer is full, stop sending data. And then what pipe will do, it will stop sending data and will not overload that buffer. Okay, so that's basically, a backpressure system. Now, this is nice if we are writing and reading from files. What do we do, in the general case where we have our own, implementation of, some processing that is not written as a Node.js stream. So let's say we have some callback, okay, set immediate or await or something like that. We are basically forking some background task, and we can fork as many as we want. It's very easy to overload the Node.js event loop if we just, let's say spawn 1,000 callbacks. Very easy to do with the promise all, promise each, promise race, those variants of it. So if we don't await for those callbacks, we can just hit them again and again and again. So we need to make sure we limit the concurrency. We need to limit the amount of microtasks that we put in the event loop. Now, another nuance to this is that if we do this kind of thing and we spawn many callbacks, eventually they will finish and they will call more things. Okay? So what happens when 1,000 microtasks finish around the same time? Overload, because all of them will be, calling the event loop back, and we'll probably enqueue some new microtasks on the event loop. So we need to make sure that we don't do that. So we need to understand what is the amount of callbacks and the amount of concurrency we can put on the event loop. Or in other words, how much load can our Node.js event loop take? And for this, we have a couple of mathematical rules, which are very simple, that help us as engineers to understand how to design our system to do this. First rule is Litter's law. Litter's law is very simple. It was pretty hard to prove from a mathematical perspective, but the law itself is very simple. So the law is that the amount of clients in the system, that is the concurrency, plus the amount of tasks waiting in the queue, is equal to the arrival rate, which is the throughput, times the latency. Very easy to compute. It's all averages, so you can get it from the logs, very easy. And from this, we can deduce the concurrency that we need to have. Now, if you look at this rule, and you start to think, what of those parameters do we control? So the throughput is basically, just coming in from the load balancer or the internet. We don't control it, but we can limit it. Okay, so we can throw some traffic away, we can refuse to receive some traffic. So we have some control over the throughput. The concurrency, again, we can limit it. So we have some control over the concurrency. The latency, however, is pretty much a result of how we wrote the system. It's a result of the services behind us. It's a result of the database. So we don't really have control over the latency. Not much we can do except maybe rewrite our code. So we concentrate on limiting the rate and limiting the concurrency. That's basically how we deal with the overload in the system. Now, we need to understand what concurrency to set in our Node.js servers. So how do we compute this? There is a nice formula that is general. This is the same formula for threaded servers, for Golang, for Java, for whatever, and also for Node. And basically that formula says that the concurrency you can handle is the number of cores you have, which is the parallel work centers, times the average latency divided by the CPU time, the average CPU time per request. Okay? Where do we get those parameters? Very easy. The average latency we can get from access logs. The average CPU time we can get from monitoring. We just look at the amount of CPU usage and divide it by the throughput. Okay? So very easy to get all those numbers from your monitoring, and you just plug it in. So as an example, in Node.js, we only use one CPU because it's single-threaded. And if you have, let's say, an average latency of 50 milliseconds, and average CPU time of 1 millisecond, so it's a 50-to-1 ratio, then you would get a concurrency of 50, okay, which gives you a theoretical throughput of 1,000 requests per second on a single Node.js worker. Okay? And then from that, you can deduce how many Node.js workers you need, and of course, you can set the limits to protect your Node.js server so it doesn't go into overload. So how do we protect our Node.js servers? Easiest way is to use a proxy. If you have Nginx or something like that, then it's very easy to set those parameters. And if we know that we cannot go over 100 concurrency, then we just set max connections, 100, we're done. Okay? Our Node.js is protected, and we don't need to do anything except that. Of course, the world is never that great. Many load balancers and proxies do not support this. In particular, Ingress in Kubernetes, even though it's sometimes Nginx, does not support this configuration without some deep customization, so we're kind of fucked. So what do we do instead? We can use a middleware. Okay? So if you're using Cora, Fastify, Express, anything like that, you can just write a middleware. There are also a couple of them in NPM. You can find some of them. I'm not super happy with the quality, but they do work. And basically, if you put a middleware and you want to make sure that it's the first middleware, okay, you can basically keep a counter, and if that counter goes, basically you increment that counter every time you get a request before you start handling it. If that number goes over the maximum number of concurrency, you return HTTP 503, which is a special HTTP status code that basically says, I'm overloaded, don't send more traffic. Okay? And all clients should know that code and basically respect it. Now, the idea here is that although we already receive that traffic and it does consume some resources within Node.js, it doesn't consume as many resources as if we started to actually handle this traffic and open database connections, connections to the upstream, allocated memory, and so on. So it actually matters where we have those requests waiting. So once we have Backpressure implemented within our system, then eventually we'll have all of our services rejecting traffic, and the gateway that receives the traffic from the client will need to decide what to do with the excessive traffic. Okay? So if we can only handle 1,000 requests per second and we have 2,000 requests per second, then we need to decide what to do with the extra 1,000 requests per second. What can we do with the excess traffic? This is the world of load management, which warrants a talk on its own. But just to give you some ideas what we can do, easiest thing to do, we can reject the excess traffic. We can return 503s to the client and let them decide what they do with it. We can also slow down the clients, but that requires cooperation from the clients. So there was, again, a special HTTP code for this, 429, with a header that says, this is how much you should wait before you try again. Okay? But again, requires cooperation from the client. If the client does not cooperate, we need to protect ourselves. Another common thing to do is to fall back to cheap responses or static responses. If you have some kind of recommendation service, then you can just give slightly worse recommendations, but which are easier to compute. This is actually very common. All search engines do this, for example. You can also fall back to cached responses and so on. But the idea is that you just give back responses that still make sense, but are maybe not as good. So that's another thing you can do when you do load management. So finally, let's just see what we learned here today and where we can go further with this. Use streams where you can, where possible. Always await for all the callbacks, the synchronous callbacks that you created, and if you used promisal or anything like that, then make sure you limit the concurrency, how many parallel tasks are being executed. There is an NPM model for this, plimit. If you don't know that one, look it up. Make sure you, make sure you calculate the maximum concurrency that you can handle, and always backpressure between services, limit all the queues, and of course, load chat at the edge of the system. It's important to do it at the edge before it consumes too many resources. This QR code here is a link to a page where I put up resources, more presentations and stuff for you to read if you want to go and learn more about load management and Node.js overload and how to handle it. Also, I put some links to relevant NPM models and that kind of stuff there, so just feel free to go and look for this. So, thoughts so long. Thanks for all the strings, and feel free to come talk to me afterwards if you're interested in that.